In a previous video, we covered sections 1 and 2 of chapter 7.3. This one should be a little bit shorter and cover sections 3, 4, and 5. Remember that today's lecture is a little shorter when we get to kinetics later in the week, because those are going to be a little longer. So first, the Curtin-Hammett principle. I'm going to start with a reaction coordinate that you've probably seen many times. That seemed to be showing through, so let me make a change there. Energy on the y-axis, and then this is reaction progress. Now, what we're accustomed to seeing is the reactant can go to intermediates and these can go on to products. But there's something special that you need to notice about this particular diagram. Unlike, say, for instance, in an SN1 reaction where the intermediate, the formation of the intermediate is the slow step, in this case it's the transformation of the intermediate into product that is the slow step. So in this scenario, intermediate 1 actually will return to reactant at a faster rate than it moves on to product. And it can then, the reactant can become intermediate 2, and of course intermediate 2 can go back to reactant. So what is happening here is that we are interconverting these intermediates before the formation of the product. Now, these intermediates can be structurally related intermediates. They can be isomers, all the different kinds of isomers, stereoisomers, structural isomers. They can be conformers of the molecule that lead to different products. And so what we want to do now is we're going to focus on this part of the diagram. We're going to take that out, and that will be found from your textbook in section 7.11. Change the lighting a little bit there. I think that makes it a little clearer. So again, this is figure 7.11 from your textbook. And here we see we have these two intermediates that are interconverting. Notice the barrier to interconversion between the two intermediates is lower than the barrier that leads to the two different products. Now, the details of how the intermediates interconvert are not critical. Obviously, it's slightly different here with the implication of there's a direct interconversion from intermediate 1 to intermediate 2, whereas in the previous diagram, I showed you the intermediates interconverted by returning to reactant and then going back to the other intermediate. Now, there are many different ways that this might happen. If this were just a conformation, it would be a simple bond rotation, for instance, might interconvert those. Okay, but again, key is that the barrier to interconversion of the two intermediates is lower than the barrier to the formation of the products. And so we can have very different scenarios. You see, we might be able to observe intermediate 2 because it's lower in energy. We might not be able to observe intermediate 1 in the reaction, or we might be able to see both of them in the reactant. But we would see more of intermediate 2 than we would intermediate 1 because intermediate 2 has a lower energy. And so there would be an equilibrium between those. Now, again, we're showing the unusual case here because those are the ones that are interesting and teach us. Intermediate 2 is lower in energy, but it has a higher activation barrier and then leads to the product that is higher in energy than the other product, product 1 being lower in energy. So if we have a reaction that is under thermodynamic control, we will see more of product 1 than we would of product 2, even though we see more of intermediate 2, because under thermodynamic control, everything is going back and forth, and it's just delta G0 that matters. Now, if we're under kinetic control, again, our intermediates in Curtin-Hammett conditions are interconverting rapidly on the time scale of the next step of the reaction. So in this case, under kinetic control, it's the difference in these two energies. So in the scenario depicted here in figure 11, thermodynamics favors product 1. Kinetics also favors product 1, but they can have a very different ratio, because here now delta G and the difference between the two delta G's, so of course that's delta G, transition state, which is the difference in energy between the two delta G transition states here. The one for the formation of 1 and the one for the formation of 2 will govern the ratio of products when we have kinetic control of the reaction. Okay? And of course, this is delta G0 is thermodynamic control. All right. Now, section 7.3.4. PMR, you'll often hear it referred to. This is the principle of microscopic reversibility. Okay, PMR is the way you'll often hear chemists refer to it, seminars or just in casual conversation. So the principle of microscopic reversibility, in its simplest statement, is that the forward reaction is followed in reverse. Okay? That is, the transition state we followed to get to intermediate 1 in this reaction, and then the second transition state that leads to product. If we reverse through intermediate 1, we will follow that exact same path with the same transition state and the same coordinates. Of course, this is a reaction that has two intermediates, the way the one we just discussed with the Curtin-Hammett conditions did. And it's a higher energy path to the second intermediate that then will quickly again lead to product. Okay, and so in this illustration, there are two potential pathways and then two potential intermediates in the reaction. Of course, if I2 is sufficiently high in energy, we won't follow that pathway. We'll follow the low energy pathway. Again, the principle of microscopic reversibility would say then, if we only follow intermediate 1 in the forward direction, we can only follow intermediate 1 in the reverse direction, that is, for the equilibration between the reactants and the products. So this is the principle of microscopic reversibility. And so it means we can often study reactions in the reverse direction where we couldn't, for instance, study it in the forward direction. So we can study hydrogenation of an alkene as a way to get insight into the dehydrogenation of an alkane, for instance. This is the principle of microscopic reversibility, section 7.3.4. And then finally, we'll only touch on 7.3.5 quickly. This is kinetic versus thermodynamic control. Again, we've been using this, but to illustrate it, if we're under thermodynamic control, these are typically high reactions conducted at higher temperatures than those that are under kinetic control. That's typically done at a lower temperature. Sometimes it can have to do with controlling the reactants proportions. Also, for instance, in the generation of enolates, there's a great illustration in a connections for you in your textbook on that. So again, under thermodynamic control, it's delta G0 that governs the reaction. Under kinetic control, it's delta G, transition state, not delta G0. And so it's that difference that will govern it. So in our illustration here, there's a larger kinetic difference here, even and with a large thermodynamic difference. All right, we'll start section 7.4 next time.